All right, good evening, class. So let's get started. So last week, right, we reviewed a number of basic concepts. Start with what is the system, talk about the input and output, what is control, what is feedback, superposition, Laplace transform, transfer function, poles and zeros, stability, and the concept of state. The many of them, right, basically it's a warm-up class. You have learned many of them when you were undergraduate. Now, right from this long list of concepts, if I want you to just choose one of them, which you think is the most important concept for control theory, which one will you pick? Okay, I heard the answer stability. How about other thoughts, other answers? State. Remember, our most important concept for control theory. We're talking about the fundamental principle behind the control theory. Which one? Has to be feedback. Okay? Control is about using feedback to change. Use feedback to change. So feedback is the key to change the behavior of the system. Okay, we can make unstable stable, right? So we use an example to show that. Then last time we use the robotic manipulator, right, to show how we design a system for the manipulator to stay upright. So let me show you a short video clip about. There are some setups about the inverted pendulum. This is a basic control problem for the kind of a textbook one, right? Because remember, this inverted pendulum is just a one-link robot arm, right? But for other robots, you might have multiple links, but the basic principle is there. If you know how to control one link, then you will know how to control the other links. But some of you who are studying the robotics, then you will know that. You can balance in the upright position using state feedback controller. Then if there is a disturbance, right, that's some external disturbance, there is a touch, but then it can still balance. This one is about it's not about the disturbance. When you design the controller, you assume there is no curve, right? But when you add a curve, actually you change the physics system. So in other words, you design a model to build a controller, but the model has changed. Some of the parameters has changed. You don't know that, but it can still handle it. So for a small change of parameters, the control system can still cope with that. Okay. First, we'll show you the way. There is a simple way to do it with a non-linear controller, right? Very simple. But we know when we try to implement that, we may have some problem. Okay, then we say, okay, let's say we can only implement a linear controller, then we do a linearization. So let's assume that the deviation from the upright position is small. Then we linearize the original nonlinear system into a linear system. Okay, once you have the linear system, we have all the tools to use. Right? We can use the Laplace transform, then we get the transfer function. So this is the transfer function, describe the robotic manipulator. Okay, and now then we want the output go to 0, right? Y go to 0 means the theta will go to pi, stay upright. Okay, and this is the feedback. So you measure the angle, right? You compare with the desired output, and then get the error signal. You try to minimize that. So we want to bring the system output to 0, or the upright position for any small non-zero initial conditions. Okay, then we first tried the open loop control. Then we say, okay, if we use open loop, okay, this is the transfer function of the system, right? This is the transfer function for the controller, and then this is transfer function for the plant. Then you multiply them, and also we discuss whether it is possible to choose the controller such that the whole system is stable. Do you still remember the conclusion we have? Possible or not? Can you make the unstable system stable by open loop? No, right? No. And we also discussed, right? We tried. This is our wishful thinking. You may try, okay, I don't like this s minus 1. I want to cancel it out, right? And then in the class, I show you this transfer function is not the same as this transfer function, okay? And we showed it, right? Using the differential equations, because we are not familiar with the transfer function, but we have a complete knowledge in the time domain, so therefore we know what's happening. And then we show that for those two transfer functions, and then there's two ordinary differential equations, we know we compute the output, right? We'll compute the solution when the input is 0. And last time we also mentioned that for any system, the response will be caused by there are two parts, right? One is what we call the zero state response. Okay, the response due to the input. Only the other one is the response due to the initial condition when there is no input. So we compute, in that example, we compute the solution to those two differential equations where the input is 0, right? We show that actually this term, if there is no input, this term will be different, right? From each other for those two transfer functions. We didn't show the first term. The first term is the response due to the input only. But now it's time for me to ask you this question. How about this term? The zero state response. So last time we showed, okay, if we compare those two transfer functions, this one is different, but when if there is no input, we show that for this transfer function, the corresponding system, right, is a stable one. The output will go to 0, but for this one, the output will blow up. Okay, but this is the solution when there is no input. But now let's come to this term. This term, that's the output due to the input, right? It's described by H transfer function times U. So now let's just compare those two. So therefore, I have an input, right? Let's say that the initial condition, this term is 0, so this is output. This transfer function times U, and so this system will be this transfer function times U. So there are the output due to the input. Look at that. Tell me. All right. I already give you actually the answer is actually the same. If you don't quite understand, okay, imagine, right? The simplest case, the input is a impulse signal, so therefore input the Laplace transform is 1, right? Then you just compare those two Laplace transform. Now they are corresponding to the signal, right? You want to do the inverse Laplace transform, get the signal, they will be the same. Is that clear? If those two will be the signals, right? Of course, they are the same. Only when, if you want to call them not a signal, they are the transfer function. And also we know transfer functions have some special meanings. They are not just the, the signals. Sometimes they may considered as the impulse response, but mainly there is a description of the system. For every transfer function, there is a corresponding differential equation. Okay, if you take that point of view, then those two are not the same. But when we talk about the signals, they are the same. Okay, any questions? Okay, good. Now, so therefore now you are clear that the output will be caused by the input and also caused by some initial condition, right? If the system is stable, what will be the steady state value of the zero input response? If the system is stable, if there is no input, what will be this term when time goes to infinity? We'll go to zero, right? We'll go to zero for stable system. So therefore, it is possible to cancel out the poles and zeros if the whole system is stable. So you can cancel out the common poles and zeros. Okay, it's a good approximation because we know, okay, anyway, so this term will go to zero, but we know this term, whether you cancel them out or not, right, they will be the same. Okay, so now I give you a situation. Okay, there are common terms, but the whole system is stable, so therefore this transfer function actually is very close to this one. Of course, the underlying differential equation are not the same, but they are almost the same if we look at the outcome. Therefore, we have one rule to state where when you cancel out this the same poles and zeros, if the whole system is stable, then you can cancel out the common poles and zeros, such that the reduced transfer function is a good approximation of the original one. Actually, that will be also the way we can describe a higher order system using approximately lower order system. Okay, we will show that later in this course. Now, let's look at another example. I want you to stretch your mind this time. Okay, this time there is a different situation. Okay, here is the transfer function. Now I design my controller in this way. 1 over s minus 2. And let's compute the transfer function. So we know the transfer function, of course, will be this one, right? This one times this. And then this time, we also have a common factor, s minus 2. Should we cancel out this common factor, s minus 2? Yes or no? You hesitate, right? So, okay. So whenever you have some trouble because you are not very familiar with the transfer function, we can try to find out the answer from the time domain, right? From the time domain, then you will be clear about the answer. Okay, let's try to write down the differential equation relating the input and output, right? This is described by this transfer function, right? So this is relating the input and output transfer function. And then easily we can write down the differential equation. Okay, we put this group, the input output, and we know, okay, s squared, that will be a double derivative. This is the way we can write down the differential equation. Okay, any questions? So remember, right, s means differentiator, right? Now then let's write down the transfer function. Let's write down the equation relating the reference signal r and the input, described by, right, the input equals 1 over s minus 2 times r. The corresponding differential equation, right? Let's put this S minus 2 on this side, right? We get this one. Therefore, this S, there is a differentiator, right? U dot minus 2U equals R. Now, because we want to get the transfer function, right, from R to Y, then we just try to get the differential equation relating R and Y. Now you look at those two differential equations. What is the differential equation relating Y and R? Just looking at those two equations should be very clear, right? What is the equation? Y double dot minus Y equals R, right? So you just look at this equation, then what is the transfer function? 1 over S squared minus Y, right? So this must be the transfer function because we derive it from the differential equation, right? We didn't make any mistake. That must be the answer. Then in this case, right, actually, in order to get the correct answer, we have to cancel out S minus 2. Okay. Now, I guess many of you probably already get confused, right? Let's take a close look at those two examples carefully. On the right side, right, we say this one. On the right side, this S minus 1 cannot cancel out. Oh, sorry, on the left side. The common factor S minus 2 cannot cancel out. On the right side, in this case, actually, this is the correct answer. This S minus 2 should cancel out. Then, what is the difference between these two common factors? Or what's the difference between those two situations? And when should we cancel them out? The answer lies in the different ways of these factors, to be associated with the signals. Can you figure it out? So, okay, this one, I want you to take a moment to think. If you know the answer, you can just tell me. Anybody want to try?
Just like inputs in the chain. Like the differential part is
Differential part goes to the input. Okay, actually, you are very close. On the left side, this differential part, S minus 1, operates on which signal? On the R. Okay, I think his answer is close to the part, but let me try to elaborate that, right? Look at those two. Let's first look at the left side. We know, okay, if we just look at this transfer function, right, we say U, right, U, the input equals S minus 1 times R. So we know this S minus 1 is operating on R, right? S minus 1 times R means that I'm going to, in the time domain is R dot minus R, right? It's an operator. This operator will be working on R. Okay, and for this one, okay, let's try to break down. Okay, let's because we have this s squared minus 1, right? Let's break down this s squared minus 1 into two parts. One is s plus 1 times s minus 1. So if you only pay attention to this s minus 1, actually, this one is operating on the output y, right? This factor. So overall, what we have is this one, right? S squared minus 1 times y equals u, but u equals s minus 1 times r. So therefore, you can say this one equals s minus 1 times r. That's how we try to relate y and r. And we know, okay, because of the way the meaning of this s, right? This s minus 1 operating on r, here there's s minus 1 inside this polynomial, right? That will be actually operating on y. So they cannot cancel out. They are doing different things. Okay, now let's look at this case. On this side, we know, okay, this s minus 2 times r times u equals r. So we say the first s minus 2, right, operating on the input signal. How about the second one? The second one, if we write down, expand out the transfer function, right, is x squared minus times y equals s minus 2 times u. This second s minus 2 is also operating on u, right? Exactly because they are doing the same thing, right? This s minus 2 times u, here we have another s minus 2 times u. They are the same. They'll be cancelled out. They will disappear from the final expression. Right? So finally, what do we have? We no longer have this s minus 2 anymore, right? They are the same. So therefore, we only have this s squared minus 1 times y equals r. The reason they will disappear because they are doing the same thing on the same signals. Therefore, in the derivation, they will vanish. Okay? So now here we come the rule. If the common factors are operating on the same variables, they should cancel out because in the derivation they will vanish. They are representing the same thing. But if the common factor operating on different variables, they should remain. Okay? Now, okay, so what is a feedback control system? Right, we say, all right, so you want to change, right? You want to improve, okay, and then feedback, right? If you want to change, then you have to use feedback. So then feedback, what does feedback mean? It means that you have to observe the output, you have to have a sensor, you have to look at what is going on output from the real situation, right? You compare with the desired output, then there may be some error signal difference. The purpose of this controller is try to minimize this error signal. So this is the feedback. You measure, you compare, and you correct. That is the fundamental concept for control theory. How to use feedback to change. Okay, and then let's compare the open loop and the feedback, right? On this side, we know, okay, this is the transfer function C times H. If there is a feedback, actually the transfer function will look like this. Feed forward transfer function over 1 plus open loop. And we know that there are many wonderful properties about the feedback controller. But among all of the properties, what is the most important one? The important one is that it can change the pose, right? If the system is unstable, is it possible to use open loop control to make it stable? If there are poles, right, unstable poles inside the transfer function, no matter what happens, how you design this thing, I already showed you cannot cancel them out. Because you cannot cancel them out, the unstable pole will always be there, right? No. So only feedback controller can change the dynamic property of the system. Therefore, an unstable system can be stabilized by a feedback controller. But remember, you have to be very cautious to use the feedback, right? Is a double-edged sword. It also means it can also destabilize the system. So whenever a feedback controller is used, you have to carefully analyze the property of the system, because you know that the property will change because of the feedback. Okay? So you have to design your controller carefully. If you don't do it carefully, it may make the performance worse. However, if we will compare the open loop and the feedback, there is an obvious advantage for open loop controller. What is the advantage? What is the advantage? Right. It is much cheaper, right? I don't care what happens at the output. In this controller, I will save a lot of money. On this side, because of the link, right? Easily now with the block diagram is, we know we just store this link in 1 second, but in reality, how to implement that link, right? That for some complicated problem, it may be difficult or very challenging. Okay. For instance, right, you want to control the vehicle on the moon, remote control, right? How do you, sense that information, and how do you, transmit that signal from the moon to the Earth? And also there is some time delay you have to consider, right? All those things. All right. Now, then of course, this course is about computer control system. So last time we mainly mentioned about how the control system with the analog signals, right? Continuous time signals. So a simple statement is that the controller will be implemented by a computer instead of an analog circuit. But how do we convert? Let's say if you already have an analog controller, how do we change that into a computer control system? Can we simply replace the circuit with a computer? Right? Let's say you implement a PD controller with some circuit, right? And then for computer control, I just replace it by a computer program. Does that work? Let's check out all the signals. In this configure, what is the input to the computer here? Error signal. But is the error signal continuous or discrete time? This is a continuous signal. But can you feed a continuous signal directly into the computer? You cannot, right? You cannot. We know that computer now, of course, we talk about the digital computer. For all the computers, for all the laptops, digital computer only deal with a sequence of numbers. Now, so therefore we have a problem on this side. Now let's look at problem on this side. What is the output from the computer program? Also will be a sequence of numbers, right? A sequence of numbers with a discrete time signal from the computer. Then what should be the input to the robotic manipulator? Has to be a torque. The torque will be a continuous time signal, right? The torque is supposed to be continuous. So therefore, we have another mismatch here. Okay, that's why, right? In order to make it work, we need to add not only the computer, we also need to convert the signals from the continuous time to discrete time before feeding into the computer, right? And also, we also have to process the output from computer, right? We have to convert the digital signal into an analog signal. Okay. Let's first check this side, right? How do we convert a continuous time signal into a digital signal? What is the commonly used one? Sampling, right? Sampling. Easy, yeah? So, okay, I just, you have a sampler, you just extract signals at some time instance, right? Time instance. Like this. And the conversion is done at the time instance. So I don't have all the information between those sample instance. I only take the signals at those sample instance. And then, of course, in this way, the computer will interpret the signals as a sequence of numbers. Okay, those sample instance is called the sample instance, and the time between the successive, right? Each sampling is called the sampling period. We will use H, right, to denote the sampling period. And normally, the sampling period is uniform, is a constant. So we only consider the uniform sampling. Now, that's why it's easier auto sampling, uniform sampling. Then we can convert the analog signal to digital signal. Now, let's do the other side. How do we convert the digital signal to analog signal? What is the natural way of converting the discrete time signal into continuous time signal? What's the simplest way? Exactly, right? The simplest one, we put a zero order hold like this, right? At this moment, I know the signal, I hold it as a constant until the next sample instant. I get a new signal, then I hold it as a constant. Okay? But if you look at this analog signal, is it continuous or discontinuous? Discontinuous. At every sample instant, you are going to change the value. Of course, that value will be different from the previous one. Okay? Now, can we make it piecewise continuous? So why not, right? We can also do this. If there is a signal, you do signal processing. This is what we call the first order hold. Now, for signal processing, we can do this. But for control signals, for control system design, we never use the first order hold to convert the control signal from the discrete time to continuous time. What is the reason? Excellent. Here, look at this signal. Let's say this is the current signal. In order to do the first order hold, actually, I need to know the signal at the next sample instance, but I don't know that signal yet, right? Until the next instance, then I know this signal. Therefore, so this is different from simple signal processing. Signal processing, you already have all the information. Here for control system design, we have to think about the physical meaning. How do we implement that? So when we use the zero order hold, it's not because of simplicity. It's because of this cause and effect loop there. We cannot use the first order hold. We cannot use this one. We always, right, because the control signal depends upon the measured output. At this moment, I don't have the information at the next sample instance. Therefore, we should do this. At this moment, I only have this signal. I have to use it as a constant until the next instant. I have some updated information. Okay, any questions? So therefore, we are going to use the zero order hold. During the sampling instance, the control signal is a constant. Therefore, there is another question. From one sample instance to the another, if you only consider that interval, Is it open loop or feedback? It is open loop because you never change your input signal, right? Remember that there are many things may happen during those two sample instances, and you have no idea what is happening. Okay, of course. So normally that the better performance, right? You have to use the higher sampling frequency. You want to make sure you didn't miss, you don't miss much information between those sample instances. But also, of course, we know in reality, right? We have to also consider the cost, right? The expense. If you have a high frequency sampler, then right, it is more expensive and also costs a lot of energy. So therefore, okay, now I come to this one. We use the first order hold because we don't know the output the next day. All right. So now let's try to derive the equations, derive the state space representation for the discrete time for the computer control. Now we are going to do it, right? Using the solution from the continuous time system, and we discussed the solutions last time. Okay, let's just revisit that. We can derive the equation again. Now, how did we solve the differential equation? What was the magical tool we used last time? Remember our Laplace transform. Okay, so you don't need to take a course on ordinary differential equation. If it is a linear equation, always, right, you can use the Laplace transform to do it. You did last time, use Laplace transform. Okay, let's just do it again. So now here, of course, we know x is a vector, right? Y in this course we only consider one input, one output. So therefore, y output is just one signal, scalar. Okay, so A is a matrix, B is a vector, C is also a vector. We need a precise solution, right? Therefore, we need to consider the initial condition. If we apply the Laplace transform, there is an x dot, so that's why we have this s, and also we need to consider the initial condition. So therefore, I have this x0. On this side, right, of course, there is no differentiation, there is no s, so just ax plus bu. So easily, right, now you already have a algebraic equation, right, and then you can get the solution. You put this x here on this left side, the x0 on the right side. And then, of course, because we group this together, we have a si minus a. And then you are going to do the inverse of multiply both sides by this inverse of this matrix. That's how you end up this solution. Okay, this is just from linear algebra. Okay. Then once we have this x in S domain, then we can also get this output, right? Output is just c times x. But this is the solution in the S domain. We want to get the solution in the time domain. Then we need to know what is this S minus A inverse. Okay, here we know there is a matrix exponential. This is the matrix exponential function defined as e to the at. There is a definition we discussed why it just looks like this Tanner expansion for the scalar case. We just use that one, and also I show you this corresponds to this is the Laplace transform. So therefore, this one right in the time domain is the matrix exponential that we plugged in. So therefore, here x right in the time domain here just okay. This is the matrix exponential right e to the at times x0. Here is a multiplication in the S domain, right? In the time domain will be a convolution. That's how we end up with the second term. This is the solution for the continuous time. Okay. Now we are going to use it, right? We're going to use this one to derive the solution, to derive the state space model, for the discrete time. Let's do it step by step. Okay, but before we do that, it is also clear from this solution that the output, right, will be affected by the state, the initial state. This is what we call the zero input response. Also, if you look at this term, it just means that if there is no input, what is the response? Yes, there is indeed a response due to the initial state. This one is what we call the zero state response, right? What is the output of the system, right? So it is caused by the input. If there is the state, initial state is zero. That's how we choose those two terms. Okay, there are always two terms. One term is due to the initial condition. The other term is due to the input. Of course, this is possible, right? We can decompose into those two terms. It's only possible for linear systems. For nonlinear systems, they may be coupled. The effect from the input signal and the state may be combined together. Cannot simply put them into two terms. All right, so here we are. So we have the solution in the time domain, and now we know what is going on for the discrete time. For the digital control, we use a zero order fold. And then we try to figure out, right, what are the signals. So let's say at the time instant, right, sample instant tk, we already know the x, right, the state. How to calculate the future state at time t, where the time t is in this interval, right, from the current sample instant to the next sample instant, like tk plus 1. We only compute the signal in this interval. Okay, now let's do it. So this is the here. If we consider this signal, right? So therefore, the initial condition is x0. Actually, you can imagine that actually starts from tk. So that's why here x0 becomes x, the state at tk. That's the initial point. Of course, this t, right? Because when we count this t is t from 0, so therefore this t becomes, right, t minus tk from the initial point. And then this convolution, of course, this is easy, right? We just change the bounds, or the lower bounds here starts from 0. So therefore we start from the initial point, which is tk. Okay, any questions? Now, in this interval, right? Because we only are interested in the signal in this interval, is the input a constant or not? We use the zero order fold, right? It is a constant. That will simplify the calculation, right? Because this one is a constant. Actually, that is the value at tk, right? We hold it as a constant. So now we can take it out. Okay, now let's try to simplify this integral. Let's change by change of variable, right? By change of variable, this t minus tau, I will use a double dummy variable v, right? Dummy variable v, and then we want to change this expression, make it simpler. Okay, let's do it now. Because of this change, we know, okay, this e a t minus tau, okay, that becomes e to the av. This d tau, of course, d tau, this tau equals, right? Tau equals t minus v. Right, so therefore d tau becomes minus dv, right? Now this the bounds, right here, this tk, that is when tau, right? Tau equals tk, right? So therefore, in terms of the v, means this t minus tk, right? When tau equals tk. Now here t, when tau equals t, v equals 0, right? So that's therefore Here from t minus tk to 0, there is a minus. So I just change this bound from the lower bound to the upper bound. Then the minus sign disappear. But you can say this expression is simpler than this one. Okay. Any questions? Okay. Here, this is what we have. This is the way we can compute the state vector in those intervals from tk to tk plus 1. Now, what we are interested is just in the final state. What is the state at tk plus 1? Okay, so in that formula, then we just replace t equals tk plus 1, right? Here is the t, now becomes tk plus 1. This t becomes tk plus 1. This is the formula we can use to compute the state, right, at tk plus 1. How do we compute the state? Right, it depends upon the current state at tk, right? Depends upon this input signal utk, because we know that input signal is a constant. Now, we know, okay, it's a periodic sampling, and then the period is h, a uniform sampling. So therefore, actually, tk is, the case sampling instance, right? The real time is just k times h, and tk plus 1 minus tk is h, right? Okay, so here we can simplify this expression. So now becomes this one is tk plus 1, right? That is kh plus h. Here, this one e to the a, right? Tk plus 1 minus tk, that is just e to the a h. Okay, here this one tk plus 1 minus tk becomes h. So we have evaluate this integral, and this one is a constant. So eventually we can say actually this is a constant e to the ah, and also this is a constant matrix times b. So we just merge that. We can just use a phi and gamma. So, and also to simplify our notation, right? When we say k plus 1, right? We don't use kh plus h. We just, okay, every sample instant is 1 unit. We have derived the state space model for the discrete time. Xk plus 1, because we say, okay, each sampling period is 1 time unit, so xk plus 1. At the k plus 1 sample instance, the state, right, equals phi times xk plus gamma times uk. So what is phi and gamma? We have the formula. This is the compute phi, right? Use the matrix exponential. This is gamma. But now, if you look at this formula, remember, right? Remember, A is a matrix, so it's not straightforward, right? This one, you need this e to the at, right? You said t equals h here, right? Actually, you need this expression, so therefore, you have to know how to compute e to the at, the matrix exponential. I mentioned one way. Do you remember how do we compute that? Tanner, not Tanner's. You cannot use Tanner series. Tanner series involves infinite number of terms. What's the other way? Laplace transform. If you take the linear systems, your lecture will give you a number of ways. But here, I just give you one way. Because this one, you know how to do it. If you have a matrix A, right, you can compute this. This is inverse of this matrix. You can do it, right? And then for each term, but you know, okay, that is in the S domain. You try to get the time domain by the inverse Laplace transform. Then you will get the e to the at. It is a matrix. Okay. Any questions? So therefore, we finally have a state space model. So for the computer control, we don't use ABC. ABC is reserved for the students that you are taking the linear systems. Okay, now we use phi gamma C. Phi gamma C. Now, last time we talked about the concept of the state, right? We're saying, what is the state? That is the information we need, right, to predict the whole future. Now let's try to verify that. How are we going to predict the future with this state space model? First, right, to predict the state at the next sample instant, this one is easy, right? It's already given there. You just do it directly. Now, then how about xk plus 2? You have this equation, right? Do you know how to get xk plus 2? You just use this equation again, right? So xk plus 2 equals 5 times xk plus 1 plus gamma times uk plus 1. Is that clear? Okay. Then you say, okay, I already know how to predict xk plus 1, right? So I just plug it in. Then you know, actually, if I know the xk, I can predict xk plus 1 and xk plus 2. Of course, we also know all the input signals. Right? We have to know the input signals. Otherwise, we cannot predict. Okay? So similarly, right, you can follow this flow. You can easily derive the expression for xk plus n. It involves, right, this term. So if xk plus n step, right, that will be the 5 to the power of n times xk. And then there are some other terms which describe the effect from the input signal. All the inputs will play its role there, right? From the UK plus 1 to UK plus n minus 1. Easily from this expression, we know that, right? The state of the system will depend upon this term that is caused by the initial state, we call the zero input response. This one, of course, that describes what is the state when the initial state is 0, right? We have this term, that's the zero state response. Now you can tell me, if you are given xk and the input signal, can you predict the whole future? You already have the formula, right? Yes, indeed. So therefore, that is another way we verify, right? Yes, this is the way. What? This is indeed the correct state space model. Okay, now then in the continuous time we have the differential equation, right? Now for the discrete time, do we have a similar description? Okay, let's look at another way. Continuous time, right, we use differential equations. But for discrete time, the discrete time signal is a signal at sampling instance, and you don't have the information between the sampling instance. Because of that, can we use the differential equation to describe the discrete time signals? How can you take the derivative? The derivative, right? You have to look, delta t will go to 0, right? But for discrete time signal, there is no delta t. The delta t is fixed. You cannot use the differential equation. So therefore, for discrete time, right, we use what we call the difference equation to relate the input and output. This is for example, right, where I can say the output at the next instant yk plus 1 depends upon the current output and the previous output, the current input and previous input, because they are linear systems, so it's just a linear combination. The output in the future is a linear combination of the inputs and the outputs in the past and the present. That's the meaning of this equation. Okay, so this is what we call the difference equation. We just use the signals, right, at yk plus 1, yk minus y. Just means, right, this is, you just consider k, this is the present, so k plus 1, that is the signal at the next instant, right? K is the current, here is the signals in the past. For continuous time, we use the differentiation operator. Okay, for discrete time, we use the shift operator, right? We just try to simplify the representation. So let's define the forward shift operator Q. So we have operator, if I apply this Q on a signal Fk, actually this signal becomes Fk plus 1. The signal will be forward shift by 1. Similarly, we can define a backward shift operator. It's just Q inverse. So Q inverse Fk means, okay, I backward shift the signal by 1. Okay, now we say why we want to do this. Why? Because we want to simplify the description of the system in a more compact way. Let's say how, with the help of this operator, how we can simplify this kind of description. Let's group the output signal and the input signal, right, on two sides. And then we use the shift operator. If we use the shift operator, this yk plus 1 is q, right? Q times yk, shift operator. Of course, there is no shift. Here is yk minus 1. So it is q inverse yk. On the right side, right, is this one no shift, but here is backward shift. So q inverse uk. Okay, any questions? Now, in this way, actually, because all the terms were on the left side, they all relate to the output y. So therefore, that's why we can do it in this way. We put all those operators together, right? And then we multiply it by the output on the right side. We group the operators and then multiply by the input. So here is where we are. Now, but if you look at the expression, it involves both the forward shift and also the backward shift. But sometimes we don't like that mixture of them, right? We can use all of them are backward shift or either all of them are forward shift. Now let's say I want to get rid of the backward shift. I don't like the Q inverse. So what should we do? Yes, so you have two signals on both sides, right? You can forward shift them together. Still the same equation, right? You have yk equals uk. It just means also it means yk plus 1 equals uk plus 1, right? Forward shift them together in the same way. I just multiply, right? In terms of the operation, I just multiply both sides by q. I forward shift the signals on both sides. That still you have an equation, right? The equation still hold. Okay. Actually, you multiply both sides by q. Therefore, you end up with here on this right left side is a polynomial of q, right? This one is a polynomial of q also. Therefore, in terms of q, I can write down the equation this way. So this way a of q, so this one a of q is a polynomial of q of the shift operator. B of q is a polynomial of q. The whole equation becomes a of q times y equals b of q times u. Now, if you compare to the original difference equation, right? I write the equation this way: the output is a linear combination of the previous and current input and output signals. Imagine, right? Here I only count 2 steps. It may involve 10 steps. You will run out of the space, right, to write the whole equation. But now, if you use this way, You just need to write down the polynomials, right? So that is a more compact way to write down the equation. Okay? You know that in math, right? The notation is important, right? Such that you will simplify the derivation and also help you to understand. Okay, now it's time to talk about, right? How we're going to solve the difference equation. Okay. For example, right? For example, how we're going to solve this equation, right? We have a difference equation. How are we going to get the, let's say, I give you the initial condition of an output, and also I'll give you the input signal, how we're going to compute the output. And then recall in continuous time, right? What was the magical tool we introduced to solve the differential equation? Laplace transform, right? We also used that. Today, we know, okay, that is the magical tool. This is the Laplace transform. But if you look at the way, right, we compute the Laplace transform, of course, normally now you have the Laplace transform table. But if you forget the Laplace transform table, you have to use this way, right? All the table is computed by this formula. But for discrete time signal, can we directly apply the Laplace transform on the discrete time signal? You look at this, you need the information on all the time, right? From 0 to infinity. But for discrete time signal, you only have the information at the sampling instance, right? So therefore, we cannot directly apply. Now, then remember, I also discussed why did we introduce the Laplace transform? Why is Laplace transform so powerful for linear system? Superposition. We do it. We want to decompose it into a exponential signal, right? So we know it's because of the superposition principle that makes it powerful for the linear system. That also explains why you can use the Laplace transform to only solve the linear differential equation. Cannot use it for nonlinear differential equation. Okay, superposition principle. Here we know, okay, we cannot use Laplace transform. But how about superposition principle? Do we still have the superposition principle for discrete time linear system? Of course we do, right? We do. Therefore, yes, we still have that. And then we are going to use it as the superposition principle to introduce another tool, which is suitable for the discrete time system, which is the equivalent of Laplace transform. Okay, so with that, I will leave that for the next part. So let's have a break. Let's have a break, a 15 minutes break, then we will continue. All right, welcome back. So let's continue. We know, okay, let's review the superposition principle. What is superposition principle? Why is superposition principle so important? It's because you try to figure out the response of the system for a complicated input, right? And then you have no idea how to do that. But on the other hand, you know the output for some basic functions. So, and also you know how to decompose, right? How to express the input as a combination of those basis functions. And for those basis functions, you know its response to compute that. if the system is linear, okay, and then the input, right, is a linear combination of the phi 1, phi 2, and then also the output will be a corresponding linear combination, right, of their corresponding outputs. So that's the idea behind the superposition principle, and it only holds for linear system. The trick of the superposition principle, right, is to choose proper basis functions whose response can be easily computed. Now, recall, last time, what did we choose for the continuous time system? What did we choose as the basis function to compute the output? Exponential signal, right? Exponential signal, e to the st. And the sinusoid, right? Sinusoid is just a special case of this exponential signal, okay? And we know, okay, this is if the exponential signal is the input, then the output will also be an exponential signal, but will be modulated by a transfer function. Okay, now, therefore, if that's the case, in the discrete time, what basis function should we use? We should also try, right, exponential signal, because it works for the continuous time. Okay, so we try the exponential function, but remember for the discrete time, right, we need to replace this t by t equals k times h, right? Okay, let's do some manipulation. So this e to the st, t actually is k times h, h is the sampling period, right? This becomes e to the s kh. Now let's combine this e to the sh, right, as a symbol a, is a complex number, right, a. Then actually we have a simpler expression is a to the power k. Of course, that is also an exponential signal, but a different shape. Okay, but it's the same as an exponential signal, but in the discrete time, we use a different form to express is a to the power k. Then we can make a wild guess what will be the output. For the continuous time, we say the input is the exponential signal, the output will be the same exponential signal, but multiplied by something, right? We can also make this guess. If this is a to the k, the output will also be the a to the k, but multiplied by another factor, right, which we call function of a. But this is just a guess. We have to verify. Will that satisfy the equation? So let's verify that. Okay. Now let's just verify this for this simple case, right? For this equation which is a difference equation. Now let's put this outputs on left side, inputs on the right side, and then let's use this expression, right? The input expressed by a to the power of k, the output expressed by h of a times a to the k, and let's plug it in here. So y at k is h a times a to the k. So k plus 1, of course, is just h a times a to the k plus 1, right? So here is just a1 h times a to the k. Now k minus 1, of course, just here, this one k becomes k minus 1. Now this is the input is a to the k. uk minus 1 is just a to the k minus 1. So we want to say how we can, what h should we choose to satisfy this equation? Now the answer is very clear, right? Answer is very clear. Both sides that have the same term a to the k will be cancelled out, and then we can get this is h of a is b0 plus b1 a inverse, right? A minus a1 minus a2 a inverse. So if we choose h in this way, indeed we verify this will be the solution. So therefore, that will be a good candidate, right, to compute the output. Then the next question is, right, can we decompose any discrete time signal by the exponentials a to the k? Of course, here I can only just give you the answer. The answer is yes. It can be shown, right? We cannot prove it here. So this any discrete time signal can be expressed in this way. The question is, what is f? Right? What is f? Now f will be defined by this series. Now, if you look at this form, it just means if you have a signal, right, f of k, but what is involved in this Z transform, okay, is only the signals starting from 0. So whatever happens in the past, it has no information. Well, we only need a signal starting at 0, starting at k equals 1, k equals 2, up to infinity. And then, right, and then f0, right, there is no z, but for f1, there is z to the minus 1. It is f2, k equals 2, well, z to the minus 2. So if you, fk equal times z to the minus k, that's the expression for this fz, and then we have a name for that. We call the z transform of a discrete time signal. This is the equivalent of Laplace transform in continuous time. Now we are going to see how this can help us to solve the equations. Okay, so let's take some time to study this Z transform. Let's look at this definition. Let's do some simple calculation, right? First, we look at this definition. Remember, Z is a complex variable. Just like in the Laplace transform, S is a complex variable. The simplest signal we want to use to compute the Z transform are just an exercise. Let's say a unit impulse signal, delta k. Delta k. This is not the impulse signal for continuous time. Delta signal in continuous time, you get one value at infinity, right? 0 elsewhere. But for discrete time, right, we have this unit impulse means that, okay, at 0, you have a value of 1. But for other place, you have all the other values. For instance, the value is 0. So that's the definition. So therefore, delta 0 equals 1. For other values, delta k will be 0. Now, by the definition here, if this is the case, what is the Z transform of this delta signal? Just to use this definition, the answer is simple. What is the answer? 1. Because, right, all other values are 0. 1 has one value. F0 equals 1. Right? Is that clear? Right? Apply just directly apply definition is 1. So the Z transform of the unit impulse signal is 1. Remember, right? For the continuous time, what is the Laplace transform of the delta signal? It is also 1, right? It is also 1. That is the reason we're saying that the transfer function is the impulse response in the S domain. Okay, that one is easier. Now let's do a little bit more complicated one. This one is related to how to compute the Laplace transform or the Z transform of exponential signal. We know that for the Laplace transform table, right, you don't need to remember that table, but one signal you should know. What is the Laplace transform of exponential e to the at? What is the Laplace transform for e to the at? 1 by s minus a, right? That is the only Laplace transform remember that actually can use that to compute all the other things. This one we know, of course. Today we are not going to compute this. Let's try to compute the Z transform of the exponential signal a to the k. Here, we are going to use the definition, right? Let's try to compute that with the definition. So is a to the k times z to the minus k, you sum them up. Now let's put it in this way, right? When k equals 0 is 1, right? This when k equals 1, this is k equals 2, you will go to, for k equals infinity, the infinite number of terms. Now, if you look at this series, this is what we call the geometric series, right? I mean, how are we going to sum up a series like exponential 1a to the k, right? But here is just a over z, right? A over z. Do you remember what's the little trick to calculate this type of summation? Don't tell me the formula, right? I want you to derive that. What should you do if you encounter this kind of problem? How will you compute this summation? This is the expression, right? F of z equals this one. In order to derive the solution, what should be the next step? Come on, you guys are from very good schools in the universities, right? You should know the answer. What should you do? Multiply both sides by a over z. That's the first step, right? You multiply both sides by a over z, and then you get this. And then once, of course, this is the most important step. Once you are here, then you know the next step. Of course, you have to because there are all the terms except the first term, right? So therefore, it must be this one minus this. This one minus this, right? And then you get this. Then on this side, you have this first term. Of course, there is another term that is a over the, but n goes to infinity, right? And also assume that this one, we choose this z such that make this term go to 0. Then finally, it's just 1 over 1 minus a over z. Reorganize it. That will be the expression of the z transform to the exponential signal. The interesting thing is, if you compare those two, right? Those two here, this s, e to the a, okay, a here is s minus a. Here is a to the power of k, is z minus a, z minus, but there is an additional term. There is a z in the numerator. Okay, any questions? Okay. Now, so of course, then there is a z transform table, right? Anyway, you can use, but here I want you to know how to derive those. We don't have time to do others. Now let's try to derive some other properties for the Z transform. There are many properties listed in the table, right? You can check that from the lecture notes. But one property I want to derive it here. This is related to the most important property of the Laplace transform. What is the most important property of Laplace transform? What is the meaning of S? Differentiation, right? Differentiation. Remember the relationship between the signal and its derivative. Laplace transform of y is the y, then the Laplace transform of its derivative will be s times y, and of course there may be something related to the initial conditions. Now, so in this way we know if the initial condition is 0 actually, right, and then s means differentiation. Now, similarly, right, the most important property of the Z transform is the relationship between the xk and xk plus 1. Remember, there is no differentiation. But you talk about the derivative, that is the relationship between the signal and its future, right? Its future, immediate future, but here is xk and xk plus 1. Let's try to work it out. This one, we just look at its definition. The Z transform of the xk by definition is here, right from the definition of this transform is x0 plus x1, z to the minus 1, x2 times z to the minus 2. Now, if we apply the definition of the xk plus 1, Z transform of xk plus 1 will be x1 plus, right, when k equals 0 is x1, when k equals 1 is x2, x2 times z to the minus 1, x3 times z to the minus 2. Now, we want to relate xz and the Z transform of xk plus 1. You look at the expression and you should know how to relate those two. Or in other words, right? Can you say that? What should we do on this xz to get x1? How do we convert this x1 to x1 times z to the minus 1 to x1? You multiply by z, right? Then you get that. You multiply x by z, so you get z times x0 plus x1 plus x2 z to the minus 1 x3 z to the minus 2, and then you know, okay, this one corresponding to the Z transform, right, of the xk plus 1. So immediately from this one, the Z x0 plus the Z transform, right, of this one. Now let's put it in this way. It means that the Z transform of the xk plus 1 is Z times xz minus Z times x0. Is that clear? Right. If you have any questions, right, about how do we derive that, right, you can ask me in the class. That will save you time, right? If you want to figure out by yourself, you may spend a lot of time. Right? Now, if you look at this one, now assume that the initial condition is 0. What we have? The Z transform of xk plus 1 actually is Z times xz. In other words, if we compare with the shift operator, like let's we apply the shift operator Q on xk, we will get xk plus 1. Right? So therefore, the forward time shift operator actually, right, corresponding to a z in the z domain. If you have a z in the z domain, z applies a signal that actually corresponding to a forward shift operation in the time domain. Okay, any questions? That is the most important property for the Z transform. Similarly, if there is a Z inverse, right, in the signal, right, then just means that you do a backward shift. Now, with that, we are ready to use the Z transform to solve the difference equations. For instance, now we want to solve this equation, right? We don't know how to do it, but now with the Z transform, right, we can do it. To simplify, right, the derivation, let's assume that all the initial conditions are 0. Then when we apply the Z transform, we know here, right? When we say that Z, right, if there is a shift, then we have a Z, but there is a condition, right? The initial condition is 0. Otherwise, right? Otherwise, there are some terms correspond to the initial condition. Okay. Here we want to simplify, right, the case. Assume the 0 initial condition. we can quickly get a solution. When apply the Z transform on both sides, K plus 2 forward shift twice, that becomes Z squared. K plus 1, right? We have a Z times Y. There is no shift, so we keep the Y. The UK plus 1 becomes Z times U. UK, keep the same, U, Z. Is that clear? Any questions? So you can see, again, we can transform the difference equation into an algebraic equation, right? And then you can easily get the solution of Y expressed by the input U. Okay? This is the solution for this example. Well, but what is the solution in the time domain? We get the solution in the Z domain, so we have to do the inverse Z transform. How to get it back? Of course, we know there is a formula. Again, we don't use this integral, right? This is the hard way. Then we should use the Z transform table. But when we try to use the Z transform table, what should we do? We have to do the partial fraction expansion, right? To get the simple terms. Now let's look at this example, right? Let's say you have a signal in the Z domain. I want to get the time domain signal. Then I do the partial fraction expansion, partial fraction of this Y. I will get this one. Okay. But then let's try to use the Z transform table. Okay, I have a table here. This table is on the left side, they are the corresponding Laplace transform. On the right side, right, is the Z transform. If I use, there is a signal, right, Z minus something. But anyway, this is a constant, right? This is a constant. Or let's look at here. If it's power pk, right, exponential p to the power of k is just Z over Z minus p. But we notice that for all the expression on the Z transform, there is a Z in the numerator, right? There is a Z in the numerator, but let's go back. To the partial fraction here, there is no Z in the numerator. So what should we do? I think some of you already learned this, right? How do you get the inverse Z transform? There are many ways, or at least you know one way. Here is the problem, right? If you do the partial fraction of Y, you will get this one, but in the Z transform table, there is a Z in the numerator. So how do we force the Z in the numerator in the final partial fraction? What's the direct way? Any idea? So instead of is that difficult? Little trick, I want to force a Z here, right? I have to do something on Y. So we will do the partial fraction. I do the partial fraction on Y over Z, right? I do the partial fraction on Y over Z. Then I will force. In the expression of Y, there is a Z in the numerator. That's a little one trick. This is one way. One way. So you say, okay, I can force it in this way. I need a Z, so therefore I'm going to do Y over Z. So there is a new polynomial, right? I have to put a Z denominator and then I do the partial fraction on this. That will leave me with 3 terms. Okay, and then I put the z on this side and I can use the Z transform table. Now, if we do it, you can verify, right? This on here, that is 1, so therefore delta signal means that is 1k equals 0, right? You will have 1, 0 elsewhere. And then for the other values, you can directly copy, right? This is them minus 0.5, therefore you have 0.5 to the power of k. 2, you have 2 to the power of k. Of course, here, you know, this value only because there's delta k, right? When k equals 1, I mean, when k equals 1 and other values bigger than 1 will be 0, right? So it only will be effect when k equals 0, you will have this term, right? When k equals 0, you get 1 minus 2 plus 1, right? That will be 0. Actually, y0 is 0, right? Okay. Now, this is one way, right? This is one way. Now, let's look at the other way. That one, right, is very direct because you want to force it there, but there is another way to force it there. Look, right, here is the problem, right? Here, by partial fraction, we get this, but we know when we try to use the Z transform table, there should be a Z, right? Okay, I can force it there. Okay, and then because I want to make the Z appear, so I just force a Z on the numerator and then multiply it by Z inverse on the outside. Okay, and then inside this, we know, okay, I can get the signals, right? I can get the signals for the signals in the bracket, but I have to take care of this Z inverse. So therefore, the Y is Z inverse times B. What is B? B is the Z transform here, right, in the bracket. And then we know the corresponding signal, right, of those two terms. You get use the Laplace transform table. This one, we have Z minus 5. That will be 0.5 power of k, right? This Z minus 2, that will be 2 to the power of k. So use the Laplace transform table, you get those signal V minus 0.5 k plus 2 times 2 to the power of k. Of course, we know this is for k, right? All the values greater than or equal to 0, right? We don't have information for k is negative. We don't have that, right? That is by the definition of the Z transform. Okay. Now, but what is Y? We have this V, but what is Y? Look, Y is the inverse V. What is the inverse in the time domain? Right? Backward shift. So you say, because Z minus 1, that is Q inverse backward shift. So therefore, you backward shift is Vk, that is Vk minus 1, right? Actually, you get this one, this signal. But we know, because we don't know that, you see, Vk is defined, right, for k bigger than or equal to 0. So when we use this formula, of course, you should start from k equals 1, right? Because k equals 0, I don't know the value of v of minus 1. So therefore, this formula holds, right? For k is greater than or equal to 1. Therefore, there is not the piece. What is y? 0. From the previous solution, you already know what is y of 0, right? But I want you to find out, right? Forget about that solution. Look at here, right? Look at here. The y is the minus 1 times a Z transform. And you think about the definition of the Z transform. In the Z transform, right, the first term is the initial value, f0. The second term is f1 times z to the minus 1, right? If the y is in this form, what will be the first term? The term for that constant. What will be that term? It has to be the whole series starts from z to the minus 1, right? There is no constant term. Is that clear? Okay, let me. Here is v of, right? What is v of z? V of z is v0 plus v1 z to the minus 1, y plus v2 z to the minus 2. If you multiply them, what do you get? Right? There is no constant term. That one term must be 0. So what is the initial point? That must be 0. Is that clear? There is no constant term. So easily you can say it must be 0. And also, from the previous solution, we also computed that it is 0. Okay? Any questions? By definition, this is by the definition of the Z transform. The first term is the initial point. In terms of y, there is no value, right? The first term starts from z to the minus 1. Okay? Any questions? So actually, this one, y of 0, because this is the definition of this Z transform, you just check that value must be 0. I just show that value must be 0. Okay, any questions? No. Let's apply the Z transform to the state space equation. Okay, now we can solve that, right? We can solve the state space equation using the Z transform. Let's use that property. The only one property we need to use is how do we take care of the Z transform of the forward shift, right? K plus 1. This time we want to get the exact solution, so therefore we need to include the initial condition. When apply the Z transform on xk plus 1, it is not only z times xz, there is a z times x0. So we include that. Okay. Then the other terms are simple, right? Does not require any shift. There is no z. There is no z. Now, if you look at this one, we want to get the solution of x, right? So therefore, put this x on this left side, put the initial condition on the right side. Remember, here the x is a vector. Then we put this together, then this z will be times our identity matrix minus 5 times x equals z x0 plus gamma u z. Okay? Then we can solve it, right? We can solve it, multiply both sides by the inverse of this matrix. We will get the solution of x in the z domain. Once we have this one, we can get the output. The output is c times x, right? So therefore, the output will depend upon the initial condition, also depends upon the input. If the initial condition are 0, we have this expression. Y equals C times Z I minus phi inverse times gamma U Z. Then let's put those terms together. We have this H. Now that's the transfer function there for the discrete time. Now we have the transfer function H. So the output is the transfer function times the input. The transfer function can be computed from phi and gamma from the state space model. Okay? And also, in the same way, we can say, yes, the transfer function can be used to compute the output, assuming the initial condition is 0, but always, right, output depends upon both the initial state and the input signal. Okay? Any questions? Therefore, similarly, that's how we get the transfer function for the discrete time using the transfer. Okay, now let's talk about the meaning of the transfer function. Transfer input into output. Okay, compute output from the input. And also we know, okay, if we use this, y output equals the transfer function times the input. Again, I ask the same question. Does the same input always produce the same output? I asked that question last week. You still remember the answer, right? Give you an example to show why this is not the case, right? The output equals the transfer function times the input only if the initial condition is always 0. If the initial condition is not 0, we know this is the solution, right? I just show you the solution. The output will depend upon the initial condition and depends upon the input. Again, we have, okay, this is what we call the zero input response. The other term is the zero state response. Okay, now the other meaning of the transfer function, this is the same thing for the continuous time, right? The transfer function is a representation of the system which is equivalent to difference equation. So therefore, you need to know how to write down the underlying difference equation, right? How do we get the transfer function from the difference equation? Then how do we get the difference equation from the transfer function? This is the only formula you need to remember. The meaning of Z. Z means a forward shift operator, right? Okay. Give a transfer function, how to write on the difference equation. Let's work out one example. Here I have this transfer function. I want to know what's the difference equation. So how do we do that? You do it this way. You put the output signal on one side and input signal on the other side. And with this, we say, okay, in the time domain, this Z means a shift, right? Therefore, this Z square times YZ in the time domain, what is the corresponding signal? Y K plus 2, right? It has to be forward shift twice, right? Y K plus 2 minus this one is UK plus 1 plus 2 UK. Easy, right? Now, if you know this, of course, you can go back to my difference equation how to write down the transfer function. Let's say I have this difference equation. I want to get the transfer function. Again, you have to group the input on one side and the output on the other side. And we can rewrite this one right by the shift operator. The shift 1, so it's Q. The shifter backward shift is Q inverse. The backward shift by 2, right? Q minus 2. Then we say, okay, the shift actually means Z in the Z domain. Therefore, we have the Z times Y minus Y, Z minus Z inverse Y Z. Cos Z minus 2. Use Z. In this way, you express the output by the input. Then you get, then this must be the transfer function. But of course, normally when we express a transfer function, right, we don't like the mixture of the inverse and the the other ones, right? The forward and the backward. So you'd better put it in this way. So I multiply, right? Numerator denominator by z squared. Then this is the normal standard way to represent the transfer function. Okay. Any questions? Now, let's compute the unit impulse response, right? We know this is the unit impulse signal for the discrete time. So actually, in reality, what is this input signal means? You have a input signal at 0, right, and 0 elsewhere. In terms of the analog signal, if we use the zero order hold to get the continuous time signal, right, it means you convert into continuous time. Okay, from 0 to 1, you have a constant of constant 1, right, and 0 elsewhere. That will be the continuous time signal. Okay. But anyway, we already know, right? How do we get the Z transform? What's the Z transform of this signal? What is the Z transform? That's the first example we worked out, right? What's the Z transform? 1. So the Z transform is 1. The input is 1 in the Z domain, right? Output is transfer function times 1. So actually, the output is the transfer function. So in other words, the transfer function is the unit impulse response in Z domain. Remember, for Laplace transform for the continuous time, we have the same conclusion, right? It just that is for the impulse response when the input is a delta signal. Now, what is the response to the exponential signal? You remember? If you have an exponential signal as the input, what is output? The output is also the exponential signal, right? Multiply by h of a. Okay? And now we know this or h of a, this is the transfer function. So which means you have an exponential signal as the input, the output will be the transfer function at the value of a times the exponential signal. Okay, let's work out some special things. Where a equals 1, the input is 1, right, in a step. The output is h of 1. So you have a constant input, the output of course is a constant, but multiplied by a factor. That is what we call the static gain, right? Or the steady state gain. That is the gain of a system. You have a constant input, the output will be a constant, same constant, but multiplied by the gain. And how do we compute that? For the discrete time, right? How do we compute the static gain or the DC gain? Is the transfer function at the value of, by this formula, yeah, at the value of 1. Okay, is that clear? So if there is a constant, then the output will be h, because it's an inner system, right? It's h1 times c. But what is the steady state gain in continuous time? Do you remember, right? You assume that you learned that for the continuous time. If you have a transfer function, how do you get the steady state gain? You will evaluate the transfer function at which value? Well, h of s equals 0. This is actually because of this one. For the continuous time, right, is exponential signal. You get the exponential signal times the transfer function at s. what is 1, which means s equals 0, right? You get a constant 1. That's how you get, right? When s equals 0, you get 1. So therefore, this is the easy way for you to remember how do you compute the DC gain for the steady state gain. Okay. Now, let's look at the transfer function. We know this is the formula, right? To compute the transfer function, if you know the phi, gamma, and c, of course, we know the transfer function should be a numerator over a denominator. So where is the denominator? Then we know, okay, once we know the denominator, we know how do we compute the poles, the values, which make the denominator go to 0, which means make the transfer function go to infinity, right? What are the zeros? That's the value which makes the transfer function go to 0. Now, then you say, what is the denominator? If we look at this expression, how do you compute the inverse of a matrix? Right? The inverse of a matrix is the adjoint matrix of this matrix over the determinant of that matrix. So therefore, that's where you get the denominator. Okay? So therefore, the denominator is the determinant of the I minus phi. Now, how do we get the eigenvalues of the matrix phi? The eigenvalue of the matrix phi actually, you know, okay, this is the way, right? It's also the determinant of this matrix lambda I minus phi, right? You compare this one, right? Actually, we can say the eigenvalues of the matrix phi is the pose of the system. Okay? Any questions? Then let's check out the relationship between the pose and the stability. We did it last time for the continuous time, right? We say, how do we understand this? We look at it from the point of view of the impulse response. Okay, we know the transfer function is the impulse response, right? Then we want to say whether the impulse response will go to infinity or go to 0. So then we say, okay, the transfer function, we do the partial fraction. Normally, we say if lambda is the pole, then there must be a term. 1 over s minus lambda will be a term component in the impulse response, right? We know, okay, in the time domain, that corresponds to e to the lambda t. And we want to evaluate whether this term go to 0 or go to infinity. Then we express this pose by the real part and the imaginary part. In this way, it's clear e to the lambda t becomes e to the sigma t times e j omega t, right? In this way, we understand why we need the real part to be negative. Only with sigma negative will make the amplitude go to 0, right? In all other cases, it will blow up or will be a constant. That's the way why we get the conditions for the continuous time. We say, okay, the pose has to be on the left side. Then if on the right side, it will stay unstable. If it is 0, right, it is marginally stable. Now, let's try the same approach for the discrete time, right? Let's have a transfer function. We do the partial fraction in the same way. Actually, if lambda is a pole, then 1 over, right, z minus lambda must be a component. But we know, okay, this one, right, will correspond to a term lambda to the power of k. But the question is, we want to, okay, in the continuous time, right, we express this lambda in terms of real part, imaginary part. Now, This lambda is in this form, right? Lambda to the power k. We want to know whether it will blow up, will go to infinity, or go to 0. Can we still use? Is this a convenient form to analyze whether the signal blow up or go to 0? If I still use the real part plus an imaginary part and now put it into a power of k, will that be convenient for you to analyze? No. So what should you do? How to express a complex number? What are the ways? Instead of using a real part, imaginary part, what is another way? What is another way? Exponential form, right? The Euler formula. I use the complex number by magnitude times, right, this e to the j theta. Theta is the angle. I use the magnitude and the angle. In this way, and then I can express the lambda to the power of k is the absolute value of the magnitude power of k times e to the j theta k. In this way, you will immediately know. Of course, this term is always a sinusoid, right? Pure imaginary part. What determines whether it blows up or not will be decided by the rho, the magnitude. So when will this rho to the power of k blow up? Greater than 1. When the rho is less than 1, go to 0. Is that clear? Okay. So therefore, remember the key difference between those two are in the continuous time, you look at the real part. For the discrete time, you should look at the magnitude of the complex number. So this one decides that stability. Because this term is purely oscillation, this is the criterion, right? Has to be less than 1. Or in other words, it has to be inside a unit circle in the complex plane. Bigger than 1, it will go to infinity. Of course, is equal to 1, we know what k will be 1. That is marginally stable case. Okay? Now, so when you look at the stability, I know that you always remember has to go on left side of the plane. Remember that is only true for the continuous time. For computer control, you have a different conclusion, but you understand them from the same point of view. You look at the impulse response. But there is some other complicated case. That is where you may have multiple poles at the same position. For example, this is just an example to show this, right? If you do a partial fraction, not only 1 over s plus 1, you also may have a square in the denominator. It means you have the pole, the same pole, the two poles at the same place. Okay, if the lambda is the multiple pole, then this, which means, right, this 1 over s minus lambda square must be one component. If you look at the transform table, right, for this one actually means that there, instead of e to the lambda t, there is a t factor, t times e to the lambda t. Then we want to know whether this blow up or not. Okay, then still we use, this is the continuous time. We do it first for the continuous time. We look at the real part and imaginary part. So therefore, then we still, if we plug it in, then we have t times e to the sigma t times e j omega t. We need to analyze whether this term t times e to the sigma t go to infinity or go to 0. Now first, if sigma is negative, we know t will go to infinity, but e to the sigma t will go to 0. If we multiply those two together, will it go to 0 or go to infinity? Will go to 0, because the rate it goes to 0 is much faster than t go to infinity, because it goes to 0 exponentially, much faster. Still go to 0, okay? Of course, if sigma is positive, both of them go to infinity, right? So no question. Unstable. But when sigma equals 0, we know that if it's a simple pole, it's marginally stable, right? But now, in this case, when sigma equals 0, what would happen? When it goes to 1 or goes to infinity or goes to 0? To go to infinity because we have a t. Okay? Since this time, actually, it is no longer marginally stable. It is unstable. Okay? That can also explain why the double integrator is unstable. 1 over s squared is unstable. You have a double pose at 0. Okay? Now let's look at similarly for the discrete time. If I have multiple poles right at the same place, it means that we have a z minus lambda square in the denominator. It means k times lambda k to the power k is a component of the impulse response. Now we use the exponential form, right, for the complex number. Then we will end up with this. So therefore, it's k to the rho to the power k. Decide the stability. Easily we can check, right, when the rho is smaller than 1, this goes to infinity, this goes to 0, but this one goes to 0 much faster than k goes to infinity. Still goes to 0. When the rho is bigger than 1, both of them go to infinity. It's very clear. Of course, when rho equals 1, it will go to infinity because of k. So it is again unstable. Okay? So let's summarize the stability criterion. For continuous time, you look at the real part, imaginary part. If the real part is negative, no question, stable. If it's positive, unstable. If it is 0, okay, you have to be careful. If it's a single pole, marginally stable. If it's a multiple pole, which means it's a repeated pole, it is unstable. Similarly, for the discrete time, you no longer whether it is positive or negative. You look at the magnitude, right? Whether it's inside the unit circle, stable, outside the unit circle, unstable, on the unit circle. Then you have to know whether it's a single or multiple. Single, it is marginally stable. If it is multiple, it is unstable. Okay? Any questions? Remember, for control system design, marginally stable is not considered as stable because it's dangerous to put a system marginally stable, right? A little disturbance can put it on the unstable side. Okay. Now we know that the poles decide the stability. Then how about the zeros? The meaning of zeros, we know, okay, if you have a transfer function, right? If we do the partial fraction, we know, okay, the poles decide the denominator. But the zeros will decide the weights, right, for each component. So the zero decides the weights for the components in the impulse response. And also, there is another important meaning for the zeros. Remember, this is the formula. We have our exponential signal, right? And then we know that the output will be the transfer function at the value of a times the exponential signal. What does that imply? Imagine, what is the output if a is the zero of the system? Which means h of a equals 0. What will be the output? Output will be 0. Therefore, we can use that way. That's what we call the signal blocking property. For example, h1 equals 0. It means, right, you can apply when a equals 1, right, is a constant or a step. What it will be the output? Output will be 0. You have applied a constant, it has no effect on the output, no response. And sometimes we need this, right? We need this property. The effect of the input can be completely rejected. When do we want this to happen? For noise or for the disturbance, right? Therefore, if there is a wind blowing on the antenna, you want the antenna to stay, right? The position does not change, right? Which means you need that particularly effect, right, to be rejected. So later we're going to show how we're going to use this for disturbance rejection. The zeros are related to an important concept in control system design. There is an inverse of a system. Let's define that. If a transfer function of the system, right, is H, right, is defined as Q over P, the inverse of a system is just we switch the poles and zeros, just 1 over the transfer function, so it becomes P over Q. The inverse of a system can be imagined as an original system with the inverse direction of the signal flow, right? The input becomes output while the output becomes input. So mathematically, we say the output is H times U, right? The input, transfer function, you get the output. Inverse, right? We say actually, if I rewrite this one, input is 1 over H times Y. So it's like the output becomes the input, right? And then the input becomes output. Of course, you will say, hey, it may not have meaning, right? The inverse of the system may not have any physical meaning. When you drive the car, your input is your steering wheel, right? The output is the heading of your car. How come you cannot say the heading of the car decides my steering wheel? Does it make sense, right? Well, because of the cause and effect, right? You cannot say the input can just become the output. No, but this is a mathematical concept which can help us for the control system design. And then we will need that later, but here we just introduce this one. It has some mathematical meaning. Okay, let's say the inverse, if the transfer function of system is Q over P, the inverse of the system is just the inverse of this transfer function is P over Q. Now the system with stable, then we can define a system with stable and unstable inverse. The system with stable inverse, which means 1 over H is stable, which means all the zeros are stable. So, okay, so all the zeros, its magnitude are all smaller than 1. The system with unstable inverse means that the system contains at least one unstable zero. Now, by this definition, let's say if a system has unstable zeros, does it imply that the system is unstable? No, right? No, it just says the zeros are unstable, okay? The concept is important for controller design. We are going to use it in chapter 4. Now, let's try to understand the relationship between the poles of the continuous time and the sampled system. What happens to the poles after sampling? So we have the continuous time, and then we do the zero order hold, right? And then we'll do the sampling. Zero order hold, right? We derive the corresponding discrete time. We want to find out the relation between the poles of continuous time and the discrete time. But first, right, imagine you have a system, right, and the system is stable, right, and then you do the sampling, you extract the system, right, and then you get a sampled system. If the original system is stable, by sampling, the sampled system must be stable, right? Sampling does not change the stability. So you can imagine, okay, the formula should tell us that if the continuous time is stable, the discrete time must be stable, right? Otherwise, I cannot explain. I have a system, I do the sampling, how come I make it unstable, right? The sampler will not change, but we want to show it, we want to show it, and then we want to come up with a formula to compute the poles, okay? Let's try to derive the formula. We have the relationship between the phi and the matrix A, okay? And then we want to use this relationship to derive the formulas relating the poles in the continuous time and the poles in the discrete time. So, of course, we know the poles, right, are related to the eigenvalues. So therefore, what are the eigenvectors and the eigenvalues of A? We say this is the definition for eigenvector. This is eigenvalue, and we know eigenvalues are the poles for the continuous time. Also, the eigenvalues for the phi will also be the poles, right, for the discrete time. The meaning of the eigenvector, that is the vector which right after the transformation, it will not change its direction, right? Only change its scale, right? Keep that in mind. Now we want to verify if V is the eigenvector of this matrix A. We want to verify is V still an eigenvector of this matrix phi? Then we need some calculation, right? Let's do the calculation, right? For this calculation, we need the definition of this matrix exponential, right? Normally, those definitions are useful for theoretical derivation. Now, we use this to try to find out whether V is the eigenvector of phi. In order to find out, of course, we need to multiply phi to the V, right? We want to find out will the direction of V change. So let's do that. Phi times V. By the definition, right, we multiply those V to this whole series, we get the V. The second term is AH times V, right? This one is A to the power of K, HK over K factorial times V, okay? And up to the infinity. Now, remember, right? V is the eigenvector of A. So therefore, A times V is lambda V. A to the power of K times V. Because remember, this one is a scalar, right? I can put it in the front. So therefore, we can compute A to the power of K times V is just the lambda to the power of K times V, because V is the eigenvector. Now, with that, we can rewrite phi times V is V plus H lambda, right here, AV is lambda V. A to the power of KV is lambda power of K times V. Okay, I put those V on the right side, and actually I put all the terms, right, all the coefficients, right, to this bracket. If you look at this one, what is this? That's the Taylor series of what? Of the exponential function, right? E to the H lambda. Is that clear, right? So here we use that one. So actually, you see, we have the conclusion. If V is the vector of the matrix A, will show that V is still an eigenvector, right? But the eigenvalue change, right here, the eigenvalue is lambda. Here, this is eigenvalue, is E to the power of H lambda. What does, so therefore we have proof. If lambda is the pole, because eigenvalue of A, right, is the pole of a system, then in the continuous time, lambda, the pole will change to the poles in the discrete time by this formula. Okay? And at the beginning, right, I asked you, if a system is stable by sampling, it cannot make it unstable. So this formula must verify that if the pole is stable, it must be stable for the discrete time, right? We can easily check that. Right? We can easily check that. If lambda is the pole, sigma plus j omega, right? This will be the pole for the discrete time. If sigma is negative, which means the system is stable, right, for the continuous time, for the discrete time, e to the h sigma, if sigma is negative, what will be the value? Will be bigger than 1 or less than 1? Of course, will be less than 1, right? If sigma is negative. Okay, so therefore we verify that, right? This is the mapping from the continuous time pose to the discrete time pose. Under this mapping, we can easily, compute some of the case, like those are the poles, right? All the square mapped into the square. You can see that all those poles, of course, this is continuous time, they are stable. They mapped into the poles inside the unit circle, right? Those are the stable poles. Here, those are the unstable poles. They map to the poles outside by this formula. Here, okay, those are the poles. Let's say they lie on those, lines. Of course, this is a nonlinear map, right? They're mapped into some curves, but those curves were inside this unit circle because those lines are stable, right? Here inside, there must be a stable pose. Okay, here also those circles mapped into some nonlinear curves inside this unit circle. Okay, but those, how to map that, those are not important. The important thing, right, is this one. If P is a stable pole, is it stable in the discrete time? It must be. Otherwise, we must make a mistake, right? Because physically, we know only sampling cannot change the system stability, right? So of course, if unstable, it must be unstable in the discrete time. You can easily check that, right? If sigma is positive, of course, this E to the H sigma must be bigger than 1. Okay, the map of the poles, right? We have this simple formula. But how about zeros? Can we use the same map to get zeros? In that derivation, right? We only show how do we get that? We use the eigenvector, right? Eigenvector and eigenvalue. And we know for matrix A and phi, right, those eigenvalues correspond to the poles. So we know for the poles, they correspond to eigenvalues. There are simple relationship. How about zeros? Did we ever mention how do we get zeros from the matrix A? Can we get zeros from the matrix A or matrix phi only? We cannot. Because that transfer function not only depends upon phi, right? Also depends upon C and gamma. Okay, so it will be more complicated. But we may wonder, hey, if we know the C and gamma, probably we can also come up with a formula. But I want you to say an example, and then you tell me whether is it possible to find out such a formula. Look at this example. A second order system. I have a continuous time, right? It's 1 over s squared. Now, here we have a table 2.1. This is also in the lecture notes. How do we use this table? This table means, or table 2.1, this is the table where you can get the transfer function by the zero order hold. What is the corresponding transfer function for the discrete time? Okay. For example, here you have an integrator, right, for the continuous time. After sampling under zero order hold, this will be the transfer function for the discrete time. Of course, you have to replace this Q by Z. That will be the transfer function. Q is the operator, shift operator. So 1 over s will become h over z minus 1. 1 over s squared, right? Here, this will be the transfer function for the discrete time. Remember, Q means z. But sometimes we say, hey, for some of the, how do we use this table? Here, like for a second order system, right? Second order system will only give you those values A1, A2, B1, B2. Because, okay, this is the way to understand the meaning of those coefficients, which means you have a second order polynomial, a second order system. Those are the coefficients in those polynomials. Okay. Now here, but I want to just pay attention to this one. You use this table, you can get the transfer function of the discrete time, right, for the double integrator. We get this transfer function. Okay. Now, of course, this one we can also still, we can easily check whether how to get the pose. The pose is 0, right? For the continuous time, if I use the pose, use this formula, we know, okay, when lambda equals 0, we get 1, right? That's how, if I get the denominator, right, it's simple. Now, but if we look at the numerator, right, we will want to analyze the zeros. What is the 0 for the sample system? What's the 0? Z equals minus 1. Right? Z equals minus 1. We have 1, 0. Then, what's the 0 for the sample integrator? Or can you get any 0? There is no 0, right? There is no value can make it, right, 0 unless we say s goes to infinity. Okay, that's a very special case. We don't consider that, right? So there is no 0 in the original second order system. You can see for this example, for the continuous time, you have no 0, but for the discrete time, you have 1, 0. Z equals minus 1. Zeros are introduced by sampling. If this is the case, can you tell me, is it possible to derive a simple formula to map the zeros of the system to zeros of the sampled system under zero order hold? In theory, is there any such a formula? Is it possible to find such a formula that you can translate the zeros from the continuous time to the discrete time? By looking at this example, the answer should be clear. Yes or no? Of course not, right? On the one side, I have no 0. On the other side, I have 0. How can you have a formula, right, to come up with something from nothing, right? Impossible, huh? So there is no such formula. And also, the zeros, right, can depends upon the sampling period. Okay, it's more complicated. So we don't have any formula to compute the zeros easily. Okay? But we do have a formula for you to compute the transfer function. You have a transfer function for the continuous time. You can compute the transfer function for the discrete time. Okay? And then from the transfer function, you can compute the zeros. But there is no simple formula like this to tell you where are the zeros. Okay? All right. So that's all for today. Then I will see you next week.